Your textbook puts Jupiter and Saturn together and speaks about them pretty much in parallel. I go a little bit different. I kind of talk about Jupiter and then a little bit about Saturn. Then I start talking about comparison. Jupiter averages about 5.2 AU from the Sun. Its orbit slightly elliptical, as you can see up there, eccentricity 0.05. That's not a huge eccentricity there. It's about typical. Takes almost 12 years to go around. It rotates in about 10 hours. Now, here's the interesting thing. The equator rotates in about 9 hours, 50 minutes, and 28 seconds, but the polar regions rotate a little bit slower, and the inside rotates a little bit slower. 9 hours, 55 minutes, and 29 seconds. So what's going on here? This is what we call differential rotation. You can read more about it in the textbook. But differential rotation basically means that different parts of the world rotate at different speeds. Now, how does it get away with that? All parts of Earth rotate the same speed. All parts of Venus go around at the same time, all parts of Mercury do, and all parts of the Moon do, and even all parts of Mars. So why is Jupiter different? Well, Jupiter's not solid. So different parts of it can slide past one another. The inclination is very low. It's only tilted 3 degrees. So that's much, much less than the other worlds we've talked about. So it's only tilted about 3 degrees. And the orbit is tilted about 1.3 degrees from Earth's orbit. Remember, Earth's orbit around the Sun defines the ecliptic. All the planets orbit pretty close to the ecliptic. In size, Jupiter is about 11 times the diameter of the Earth. If you measure across the equator, and about 10.5 times the diameter of the Earth if you measure pole to pole. So now, what does that mean? It means it's oblate a little bit. So that means that it's a little bit farther distance from across the equator than across the poles. Centrifugal force is flattening it out a little bit. And so that turns out to be kind of an interesting sort of thing there. And Earth is a little bit oblate as well, but not nearly as much. You can fit over 1,000 Earths inside of Jupiter. Something close to like 1,200 Earths would fit inside it. But it only weighs about 320 times more than Earth does. And so the mass is only 320 times more, even though 1,200 Earths would fit inside of it. So what does that mean? Well, it means it's made of lighter stuff. The average density is 1326 kilograms per cubic meter. Put in other terms, that's 1.33 grams per cubic centimeter, compared with Earth, which is quite a bit higher than that, closer to 5.5. So it's made of lighter stuff. Hydrogen and helium make up the bulk of this. Escape velocity, 60 kilometers per second, way higher than Earth. It's real hard to get away from because, it's got a lot of gravity. Your book gives the surface gravity as about 2.36 times that of Earth. Now, I've always thought this was kind of silly to talk about the surface gravity of a planet that has no surface. But your textbook does this. Most every other textbook does this. It talks about the gravity at the surface of Jupiter and Saturn and Uranus and Neptune. And I keep going, well, they don't really have surfaces. These are not solid worlds. So what does that mean? Well, typically for something like this, we define the surface to be the top of the cloud layers. Even though we know there's more atmosphere above that, we know that it's not solid there, there's stuff below that, but we say that's kind of the surface of it right there, because that gives at least something we can look at. Okay, and so that's kind of what they normally give, is that. The temperature at the top of the clouds is pretty cold, minus 108 degrees Celsius. That's minus 162 degrees Fahrenheit, so it's pretty darn cold up there. The atmosphere, as we expect, is mostly hydrogen and helium. It's about 86% hydrogen, about 14% helium, about 2% other 0.2% other stuff. The other stuff is things like methane, ammonia, water vapor, carbon dioxide, etc. So argon, nitrogen, all kind of other things that are out there. This far from the sun, methane and ammonia turn out to be very important constituents. Methane, which is CH4, and ammonia, which is NH3. So these turn out to be big parts of what makes up things in the outer solar system. And again, you can imagine we get all these comets, and we know comets are made out of these things, and they're going to rain into all these objects that are out there, the gas giants, and so that's going to contaminate the atmosphere with these other things. That's going to give rise to a lot of the clouds that we see out there. And in fact, that's all that you see when you look at Jupiter, is you see clouds. You see the stripes, those are clouds, bands and zones there. You see swirls. The swirls are giant storms. The great red spot itself down there is basically, the great red spot is basically like a giant hurricane right there. But there's these other storms, and these storms are all huge. These storms are all ginormous sort of things. We have dark spots there. Those are storms. You got light-colored dots. Those are storms. This is a very, very stormy world. It rotates very, very rapidly for something that size. Remember, it's rotating in less than half the time Earth does, and yet it's vastly larger. That means the outer parts of it have to be going around much, much faster, which means the centrifugal force is really big. The Coriolis force is going to be really big. And so that's going to have a huge impact on all kinds of weather here. The core is small compared to the planet. So a few times the size of the Earth. And that's going to be the rocky core. Now, when I say rocky core, don't think of it as necessarily solid, because as you squeeze inside of Jupiter, the pressure is going to be enormous, and the squeezing is possible going to make it so hot inside there that that rocky core might be molten. There's still open to debate as to whether it's molten or solid in the middle. Rocky, but all those comets hitting Jupiter containing water, ammonia, methane, all these things are typically frozen. They're heavier than hydrogen and helium, so they're going to sink to the inner part of the world, but they are not as heavy as the silicates and the iron and the nickel, which would make up the planets, the solid planets, and so that means they're going to be floating above. So it's almost like a layer, like an outer core made of liquid ices. I don't want to say just liquid water, because yes, it's going to be liquid water primarily, but also liquid methane and liquid ammonia. All these things are normally ices in the outer solar system. Now, this is the basic physical structure of Jupiter. The outer part of it, all the rest of it, is going to be hydrogen and helium, mostly. Now, what happens is that if you squeeze hydrogen enough, you actually squeeze it into a liquid state. Now, if you squeeze it even more, under the right circumstances, enormous pressure and enormous high temperature and enormous pressure and liquid, then it will start conducting electricity like a metal. Remember, hydrogen in the far left column of the periodic table. That's a type of metal over there. Those things conduct electricity. Normally, you don't think of hydrogen doing that, and normally it doesn't. Gaseous hydrogen does not. Normal frozen hydrogen does not. But liquid metallic hydrogen does. Metallic hydrogen is a very difficult thing to produce here on Earth because the conditions have to be just right. But those conditions do exist on Jupiter. And so we can have metallic hydrogen. Okay, the outermost part is going to be ordinary hydrogen helium, gaseous in nature at the top. But as you go deeper and deeper into it, you gradually squeeze the hydrogen into a liquid.